Well, many of the statistical tests that you perform require or assume a normal distribution. Sometimes the distribution isn't normal. It may be abnormal. You may have a skewed or a bimodal distribution. And sometimes your sampling strategy, if it's a randomized sample, if it's stratified, if it's a convenience sample, those may all play into what your distribution actually looks like. So here we have a couple of different distributions. On the far left is a normal distribution. In the middle is a skewed distribution. And on the right is what kind of looks like a bimodal distribution. So on the bottom is kind of a sample here, a normal, typical bell-shaped curve. The vertical line in the middle is the measure of central tendency, so it's the mean or the average. It also happens to be the median and the mode in the sample. And the vertical lines to the left and the right represent the variation in the sample. It may be the standard deviation. It may also be the confidence intervals. So it's always important to look at the labels on your graphs. So the variation is a really important factor in determining whether this sample, if it's a test for difference, if there's a significant difference, or if it's a test of relationship, if it truly is related. You'll have factors such as the standard deviation and the standard error, as well as the range and variance. More to come in subsequent stats chats on those concepts. So let's take a look at an example using my commute time. So it currently takes me about 75 minutes to drive to work each day, one way. So my average commute time is 75 minutes. And most of the time, so let's say in this case, these are my 95% confidence intervals. So 95% of the time, it takes me between 60 and 90 minutes to make that trip. So that's an example of looking at a distribution. Another way, let's say we're looking at variation. Okay, so you have a plot here on a graph of height over weight, and you can see that there's a relatively straight line relationship between these two factors. Other variables, so in this case I have weight and cholesterol, less of an association. So if you were doing, say, a correlation coefficient, this set here would have a lower correlation. This would have a higher correlation. Okay, so what are we looking for with these distributions? We're looking at the probability or the chance that if we're looking at a test of difference, that the difference between these two groups could be due to chance alone and not due to some other factors, such as maybe our dependent variable. We typically express this in a p-value. Sometimes it's represented with confidence intervals. Normally the significance level is set at 0.05, which means then that there's only a 5% chance, if it is below that or less, that the difference between these two groups is simply due to chance. Let's go back to my commute time example. So again, we know the mean and the variation. Okay, so now we're going to do my commute time during rush hour. So on the left is my normal average commute time, 75 minutes plus or minus 15 minutes. During rush hour, and this is just a fictitious, just to give you an example here. But in this case, my rush hour time is 105 minutes. It's gone up by a total of 30 minutes. So we want to do a test to see if that's a significant difference. And you can actually look visually and see that there truly is a difference, because there's virtually no overlap in these two samples. If I'm looking at my confidence intervals, my confidence interval on the right side of my graph for my average commute time is still lower than the confidence interval on the left side of the graph for my rush hour time, the group in red. So I would conclude, if I did a t-test, I would expect to find a significant difference in these two groups. Using another example, let's say I compare my morning and evening commute times. In this case, there's still a pretty significant, or I should say, the evening time is higher, it's greater. It went from 75 minutes in the morning to 100 minutes in the afternoon. But are these two times significant? And again, just with some fictitious data here, but to show you that there's quite a bit more overlap. So there actually is a chance, there's a probability that I could have a plot of data, especially right in here where I could be a member of either group. Okay, so the overlap between this curve and this curve here is great enough for us to conclude that there is no significant difference between these two samples.